today. Whew. Well, let's make the best of the sauna we can. All right, so a couple things I want to mention before I ask for questions. We are going to be able to cover 4.3 and 4.4 today. Okay, so tomorrow we'll review for the exam, and the exam will be Wednesday, right, the 24th. That's your only obligation. So here's your due dates and assignments. Notice due tonight by midnight is these two. 4.1 and 4.2, which are really pretty straightforward. 4.1 especially is pretty straightforward. And then we'll cover 4.3 and 4.4 today. We'll definitely get through 4.3. We'll get through most of 4.4. We might, there might be a little bit I'll have to touch on tomorrow during our review period, but that's where we're headed. Your review will be right here, which I've decided not to print it out, since you guys have access to it. For this one, it's 2 pages, so I'm not going to print it out. But it's right here under this paper reviews and formula sheets. Hit the drop-down arrow there. Or not on the formula sheet, hit the drop-down arrow here on the reviews. And then there's exam 2 review. Sections 3.1, sections 3.2 through 3.4. Anywhere you see this NC symbol, that means it's going to be on a formula sheet. All right? The NC actually stands for note card, which I'm not going to let, I'm not going to allow you guys to have a note card. I'll bring in the formula sheet with these formulas. You'll notice there is not the sections 3.5 and 3.6, which deal with independence and conditional probability. I'm not going to test you over those. All right? We did cover them in class. I wanted to expose you guys to them, but it's not something we do in the math department in any of our stats classes. We've actually decided to remove those. So we're not going to test you over them. But I still thought it was definitely of value to know. Because the independence especially really leads us into what we're going to talk about today with the binomial random variable. So you've got to kind of understand what independence is so that we can talk about this stuff. So 4.1, 4.2 we've already covered. Which I'll start off today just going back over 4.2 really quickly. Then we'll cover 4.3, which deals with what's called the expected value of a random variable. And then we'll cover 4.4, which if you've taken 106, you've already seen the binomial formula. Success and failure is when you take any event where you have one of two outcomes, you either have success or you have failure. You have to define it differently depending on your experiment. Okay? And we'll talk about all this stuff. Well, I know it kind of looks a lot more complicated than it actually is. It's really a pretty easy formula to use because there's only two outcomes. That's what makes it nice. There's not 27 different outcomes. There's only one of two things that can happen. Once again, I apologize for the temperature in here today. I thought they had it fixed. Any questions over 4.1 and 4.2? You guys look at them this weekend? I know they're due by midnight tonight.
Yeah, 4.2 is question number 3.
4.2, number 3? Number 3. All right, let me go ahead and snip that out. Okay. Toss 4 fair coins. Or toss the same coin 4 times, right? It's basically the exact same experiment. So that's our quest, is to toss a fair coin 4 times, or 4 different coins once each, and let X equal the number of heads observed. All right. So we can either have no heads, we can have 1 head, we can have 2 heads, we can have 3 heads, or all 4 of them actually could be heads. So the answer to this one is C. Right, does that make sense, what's going on there? And there's actually 5 different outcomes, even though we're only tossing the coin 4 times. And the reason is because even if we only toss the coin once, there's 2 outcomes, right? It could be a head or a tail. So head or a tail, so toss it once. You don't get one, right? Toss it again, maybe you get 1 head. Toss it again, you miss. Toss it again, you miss. So your experiment would have only been 1 head. So all of your possible outcomes are right here in part C. Right? That makes sense, right? What's going on there? So identify the sample points associated with this experiment and assign a value of X to each sample point. Then list all the possible values of X. Okay, so there we go. Oh, let me go back to the homework. So here, to answer this question, we need to see all of the different events, right? We need basically a list of all the different things that can happen here. So this is where we would build our tree. All right, have head, tail. So let's start up here. So here's our first toss. I grabbed the black marker that worked, and then I grabbed the other one. All right. So here's our first toss. We have one of 2 outcomes. It can either be a head or a tail. And let's go ahead and toss again. So this is our second toss. So I'm going to go ahead and write here. In our second toss, after a head, we can either get a head or a tail. And after a tail, we can either get a head or a tail. Then let's go ahead and toss again. 1, 2, 3, 4. So at each one of these events, right, after the end of the second toss, we toss again. What happened the previous time has nothing to do with what happens the next time. So each of these will have a head and a tail, then a head, then a tail, then a head, tail, and then finally heads and tails. So now we need one more toss, right? We need a 4th toss. So we need to add one more line into this tree diagram. Right here we only had 4, now we have 8 different times. And then it does the same thing. So head, tail, and this will be our 4th toss. Do it again. Kind of running out of room here because this board isn't very wide. And then head, tail, head, tail, head, tail, and head, tail. So go ahead and write that out. That's our 4-level tree diagram. We go in here to this view and example, it'll do the same thing. So here's all the different events that it has. So notice here, it's got the event where we have 1, 2, 3, 4 heads. Notice that's the event if we stay along the left side of this tree. 1, 2, 3, 4 heads. Then the next event it has, you have head, 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 tail. Then it goes head, head, tail, head. Head, head, tail, tail. See how it counts every single one? So you want to go down the tree and make sure you hit every one of these leaves going through each time. So how many different outcomes do we have down here at the bottom? We'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There's 16 different things that can happen in my 4 coin toss experiment. I could list them all out, but they're listed here, so just to save time. But the way that they come up with these is by following this diagram. See, so they have a head, 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 tail, head, head, tail, head, 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 tail, tail. All right? Maybe a little bit different. So they split it on the top head first. Head, tail, head, head. All right? So that's how they come up with all these different things that could happen. So what they've done is they've listed them in order where there's only one head. See how they have the event where there's 0, or this is actually for tails observed, so the example's a little bit different. They're actually counting the number of tails as opposed to the number of heads. So they have one event where there's no tail, no tails. We actually only have one event where there's no heads, right? When you go tail, 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 and then tail. Right? So they list them out from this tree diagram. Now, and a good way to do it is to list it and then mark out the very bottom one to make sure you've accounted for it. That's how they come up with this number, or with this set. We've done it for two coin tosses. We've done it for 3 coin tosses. We've never actually done it for 4. That was saved for this homework assignment. And I could add another level and do it for 5 homework. Or 5 coin tosses. Okay? So that's how we come up with that. Now, how many times in this diagram was there only one tail? Notice there's 1, 2, 3, 4. There's 4 different events that only produce one tail. So conversely, there'll only be 4 different events that only produce one head. Which is the same thing as the 3 tail. So this one has only one head, this one has only one head, and one head. All right, so that's how they count the number of events that produce one and only one head. Now, how likely are each of these 16 events? Are they all equally likely to happen? Is one of them weighted more than the other? No, so they're all 1 out of 16, right? The probability of any one of these 4 events happening is 1 out of 16. So, to answer the question of compute the probability that we'll have only one head, what we do is we count the number of events that produce only one head and add together their probabilities. So, 1 out of 16, and then how many of these lines go to only produce one head? How many of them we just looked at on the diagram? There'll be 4 of them, right? There'll be 4 events that only produce one head. All the other events either have no heads, 2 heads, 3 heads, or 4 heads. So the probability for exactly one head has got to be 1/16 plus 1/16 plus 1/16 plus 1/16. which if we go through the view and example, so we go, note that each sample point is found in part A is equally likely. That's very important, right? The coin has to be fair, or else we can't do it this way. Since our 16 total points, that means the event of 1 happening is 1 out of 16. So since there's 4 events where we have only 1 head, this is the events where there's only 1 tail, right? It's kind of the opposite of our question. We add together our 4 events, which is 4/16, which reduces to 1/4, which is 0.25. So what that means is we have a 25% chance when we flip 4 coins that we will get exactly 1 head. You have a 75% chance that you'll get something other than 1 head, which could be no heads, or 2 heads, 3 heads, or 4 heads. That make a little more sense after we kind of go through it that way? Now, I know the hard part is really counting all of these. All right, so we have H, 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 and then H, 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 T, then H, H. So now, this H has went away, right? We've exhausted that piece right there. That's kind of how I do it to make sure I don't forget anything. Right? Okay. So really, we could do by process of elimination. Since I know there's only 1 event, so when X is 0, that's 1 out of 16, right? There's only 1 event where we have no heads. It only happens 1 time. Right? You guys agree with that? That's over here, right? Where we get tail, 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 tail. Any other row, any other way that we would come down this tree, we would eventually hit a head somewhere. Right? If I went tail, 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 I went this way, boom, there's a head. If I went tail, tail, well, there's a head, dead tail. Right? So any other way down the tree, we would eventually hit a head. So our chances of getting no heads is 1 out of 16. Our chances of getting exactly 4 heads is the same probability, right? It's going to be 1 out of 16. So how many events are left over? Right? How many different routes down this tree are there after I count both of these? There's going to be what? 14, right? Because here's 1 and here's 1. So I just seen from my example here, my chances of getting exactly 1 head is 4 out of 16. I'll go ahead and leave it as an unreduced fraction. So my chances of getting exactly 1 head are 4 out of 16. My chances of getting exactly 3 heads is going to be the same probability. 4 out of 16. So what's my chances of getting exactly 2 heads? How many different trips down this tree are there where there's exactly 2 heads and 2 tails? Well, I could go through and count them, or I could do process of elimination. How many are there? Because here's 1 and 4, so that's 5, 9, 10. So how many are left over? 6. So that means there has to be 6 out of 16 possible ways to get down that tree where we hit exactly 2 heads. All right? And I could have done this the same way if I go through and list out every single one of my events here. If I go through systematically and list them all out. Out of the 16 events, 1 will have no heads, 1 will have all 4 being heads. So now I can compute probabilities for all kinds of stuff now that I know this. Right? I could say, well, what's the probability that you get at least 2 heads? That would be this one plus this one plus this one. Right? 11 out of 16. Or at most 2 heads. That would be this one plus this one plus this one. Okay? Let's go through. So, what's the probability for exactly 2 heads? That's going to be right here, right? 6 out of 16. Notice how it's equal. It doesn't say less than or equal to or greater than or equal to. It says exactly 2. How many events are there that give us exactly 2 heads? Well, there's 6 out of 16, which as a reduced fraction is 3/8, right? Divide both of them in half. So what's the correct probability distribution? Does this look like it's symmetric? Definitely. Right? On the two ends, it's going to be the same height. And then the two middle bars will be the same height. And then the one in the center will be the tallest of all three. So notice it'll be this one, right? How it's symmetric. So if you're doing this experiment, most likely you're going to have two heads. Right? Out of these 5 different events, the one that happens the most is getting exactly 2 heads. All right. Any other ones from this section? This is, this example kind of went in depth because I know, so here's this. 2 or 3. And this is important because it kind of leads into what we're talking about today. So that means our probability of getting exactly 2 plus our probability of getting exactly 3. Right? So that's going to be this probability plus this probability, which is 10/16, right? Or 5/8. Because 10 divided by 16 reduces to 5/8. So that's probable, right? That's more than 50%. The probability of this event is greater than 50-50. It's better than a coin flip. So that's something you would definitely bet on. Right? If you're in a casino and say, well, would you bet that you would have 2 or 3 heads and 4 flips? Absolutely I would. Because in the long run, I'm going to be correct 5 out of 8 times, and I'm going to be incorrect 3 out of 8 times. That means in the long run, I'm going to make money. Right? And the next section really talks about this in the long run idea. Okay, so the hard part with this question was listing out all of your events, like this. Really, I could go through and write HHHH, HHHT, HHTH, HHTT. So then I've exhausted those 4 and just keep going. Okay? Hope that helped. And this gives you the information. Here's a big old ugly formula where you basically had to just plug values into the formula. Order of operations is very important right here in this. And I really want to push that because the stuff we're going to talk about today, order of operations is very important. So all that stuff in the numerator, you kind of want to put it in parentheses and then divide it by this stuff in the denominator. You don't want to just type all that in straight away. Because if you do, then this piece will get divided by this piece, but that's it. And this will actually end up in the numerator if you don't put parentheses around it. Right? Because the way the calculator does it is it treats multiplication and division on the same line, which it is, but then it just goes from left to right. So you want to make sure when you put this in your calculator, you put the entire numerator in parentheses and the entire denominator in parentheses. Does everybody know where the factorial button is on their calculator? Can everybody find that? We'll actually look at it again today from the discussion today. But this is just a simple plug and chug procedure. It gives you an x value, you plug it in for x, put it in your calculator and hit enter. Okay? And then you can read through this stuff and try and answer. And you need to look at your definition of what a random variable is, right? A random variable is defined as is a variable that assumes numerical values associated with the random outcomes of an experiment where only one and only one value is assigned to each sample point. Now, they don't have to be equally likely. That's not a requirement of a random variable, right? One thing could be more likely than another, which this is an example. The event of getting 2 heads is more likely than the event of getting no heads, right? They don't have to be equally likely to be a random variable. Now, the coin has to be fair so that we can produce these probabilities. right? Each one of those events has to be equally likely, but when we cast it, X is the random variable here, the number of heads. Okay? Okay. So let's go into the discussion today, and it'll help, kind of concrete the ideas we've talked about. This is piggybacking on the same stuff. Okay? So let's go look at section 4.3. This is one of my favorite sections from the entire textbook because it's so applicable. After we go over it, you'll probably understand understand a little better about how, laws of chance kind of work. Let's go chapter 4, 4.3. This section's actually pretty short. There's not a lot to it. Okay. Expected values of discrete random variables. All right, so just that title of the section really tells us a lot about what we're going to be talking about. So we've talked about random variables. Random variables is an experiment where every event has some probability associated with it. Here's an example. My random variable is the number of heads when I toss 4 coins. Each of my 5 events has a probability associated with it. What expected values would tell me is, if I would do this experiment 10 million times, what would be my average number of heads? So I do the experiment, I flip a coin 4 times, I count the number of heads. I do the experiment again. I flip a coin 4 times, and I find the number of heads. Then I do the experiment again. I do it 10 million times. Out of all those experiments, what's my average number of heads? So do I expect to get 1.8 heads or 2.3? Now I know using a decimal, you can't have a fraction of a number of heads, but it kind of the number of heads on a coin. But it kind of helps to tell us exactly how many we should expect. And in this experiment, the expected value would actually be 2, right? We would expect if we did this over and over again 1 million times or 10 million times, that the average number of heads would be 2. We'd have 2 heads and 2 tails because this coin is fair. It's 50-50. So we would expect our expected value to be as close to 50-50 as possible. Another way to think about expected values is if I went and bet $5 at a blackjack table, right, and I follow all the rules where you hit on 15 if the dealer's showing 16, or if the dealer's showing 12, or whatever it happens to be. You follow all the so-called rules. How much money would I expect to make after playing 1 million times? Would I get back my $5? Would I lose $100? What would it be? What would I expect it to be in the long run? That's exactly what an expected value is, right? In the long run, how many heads would we get? What would be my average number of heads? Okay, so let's read through this. If a discrete, remember discrete means countable. So the number of heads, of course, is countable. Right? If a discrete random variable x were observed a very large number of times, which means if I perform my 4 coin toss experiment a very large number of times, and the data generated were arranged in a relative frequency distribution, which means, how many heads, how many did I get, how many times did I get 0, how many times did I get 1, which is exactly what the graph we looked at in your homework, that was a relative frequency distribution, right? The graph that had that looked mound-shaped where it just barely went up on the edges. The relative frequency distribution would be indistinguishable from the probability distribution. They would be the same. Thus, the probability distribution for a random variable is a theoretical model for the relative frequency distribution. So our chances of something happening is exactly equal to if I performed the experiment a very large number of times and counted the number of heads that were produced, which is really pretty awesome. The relative frequency becomes the probability as long as we perform it a very large number of times. That's the important part. Okay? To the extent that the two distributions are equivalent, and we will assume they are, the probability distribution for x possesses an average and a variance. Right? If I did this experiment 10 million times, what would be my average number of heads produced? What would I average? Right? This section explains how you can find the mean value for a random variable. We'll illustrate the procedure with an example. Okay? So the way that they do it, examine the probability distribution for x, the number of heads observed in the toss of 2 fair coins. So we're going back to 2 fair coins here. We're not using the 4 fair coins example. All right? So we're stepping back to this level right here, right? We're basically erasing this stuff. Right? We're only talking about 2 fair coins. So I'm not even going as far here. And if I let x be the number of heads produced, right? So I have 3 outcomes. I can have no heads, I can have 1 head, or I can have 2 heads. And we've shown in the past that your probability of no heads is 1/4, or no heads. Your probability of exactly 1 head is 1/2, and your probability of 2 heads is 1/4. Because as I go through this tree, I have 1 event that produces 2 heads, I have 2 events that produce only 1 head, and I have 1 event that produces no heads. So out of my 4 events, it'd be 1 out of 4, 2 out of 4, 1 out of 4. All right? So look at what they're doing right here. They're basically, they're performing this experiment 100,000 times. So I'm going to flip 2 coins 100,000 times. I would expect that 25,000 of the 100,000, that's 1/4, right, would produce 0 heads. Then I would expect that 50,000, or half of the 100,000 tosses, would produce exactly 1 head. Right? And then I would expect that 25,000 of the 100,000 tosses would produce exactly 2 heads. So I'm going to add together the number of times it appears. So I'm going to add 0 25,000 times, which is just 0, right? But you still have to do it for the formula. Then I'm going to add 1 50,000 times. Then I'm going to add 2 25,000 times. So I'm just averaging the number of heads that showed up. And I'm dividing it by the total number of throws, right? By the total number of experiments. So when I do this, when I do x times its probability, plus 1 times its probability, plus 2 times its probability. And the reason I get those fractions, if they did 25,000 over 100,000 is 1/4, 50,000 over 100,000 is 1/2, and 25,000 over 100,000 is 1/4. Because I can split that fraction up, right, and write everything over 100,000. My mean, my average number of heads in 100,000 experiments would be 1. Which in this, in this example, that seems pretty trivial. You think, well, of course, in a coin toss. What about in an experiment where I'm betting on something else? What would I expect? Like at the craps table. Well, I'd have to come up with my probability of winning a hand and my probability of losing a hand, right? And then do it however many times I played. So this is a really interesting thing that happens here. You basically take the random variable, which in this case would have been 0, times its probability, plus the random variable times its probability, plus the random variable times its probability. So let's do it for this one. That's a little bit longer. What is my average number of heads I would expect if I perform this experiment, a million times or a billion times? Notice the number of times you produce it isn't really important because it always comes back to whatever the probability is. So let's find the expected value of this experiment. So that would be 0 times 1/16, plus 1 times 4/16, plus 2 times 6/16, plus 3 times 4/16, plus 4 times 1/16. I'm basically just taking the average here. I don't have to worry about dividing it by anything because I've already formulated values for my probability. So let's do that. So my mean, mu would equal 0 times 1/16 plus 1 times, it was 4/16, right? Yep. Plus 2 times 6/16 plus 3 times 4/16 plus 4 times 1/16. So this would give me a value for my average number of heads in 4 coin tosses. If I tossed a fair coin 1 billion times, what would be my average number of heads? Now, you don't have to do all this by hand. You know, you can't put it in your calculator. I'm going to go ahead and do it by hand now. What's 0 times anything? 0, so that one goes away. Plus 1 times 4/16 is 4/16. And I'm going to leave it with the denominator of 16 so I can add all this stuff together. What's 2 times 6/16? How do I multiply those two things? I'm not looking for the decimal. How do you multiply fractions? Because this is a fraction, right? It's 2 over 1. Remember, what's the rule for multiplying fractions? No, not by their reciprocal. That's dividing fractions. When you multiply, you just multiply straight across. So 2 times 6/16 would be 12/16. Right? Because isn't 2 times 6/16? So that's this thing twice. So this is equal to 6/16 plus 6/16, right? Which is equal to 12/16. So what you end up doing is you just multiply straight across. And 2's over 1. Right? So 2 times 6/16 is 12/16. What's 3 times 4/16? 12/16. 3 times 4 is 12. Over 1 times 16 is 16. So this is 12/16 plus, what's 4 times 1/16? 4/16. All right, let's add all these together. So 0 we don't have to worry about. So here we just add together the numerators. 4 plus 12 plus 12 plus 4. What do we get? 32/16. Which is equal to exactly 2 heads. So we would expect my average number of heads on this experiment to be 2. 2 heads on average. So that's what I would bet on. Because this is what's going to happen over the long run. So let's do this. Let's do our expected value again, but I'm going to do it for 3 experiments. Or for 3 coin tosses. All right? So what would be the average number of heads we would expect in 3 coin tosses? What do you guys think? If I tossed a coin 3 times and recorded its number of heads, and I performed the experiment 1,000,000 times, what would be my average number of heads? What do you guys think? 1.5. 1.5 heads. You would expect 1.5 heads every 3 tosses. So I know it doesn't really make sense because you can't get half a head. But it does make sense when we're talking about the expected value. So basically that means getting 1 head and getting 3 heads would be equally likely. So let's do that. So we have head, tail. So this is my 3rd toss. So how many different events are there here? 1, 2, 3, 4, 5, 6, 7, 8. Which is the same thing as 2 to the third power, right? 2 outcomes, we do it 3 times. So let's write down all of our events. So we have H, H, H. So I've taken care of that one. Then we have H, H, T. H, H, T. So I've taken care of that one. So then that one's been taken care of. So I have H, T, H. So that one's been taken care of. Then I have H, T, T. So now that one and that one's been taken care of. So now that one's even been taken care of. Let's keep going. So now we have T, H, H. So that one's gone. Then we have T, H, T. Then we have T, T, H. And then, oh, well, what am I doing? Don't strike those out yet. And then finally, our last one is T, T, T. So we've counted every experiment. So if our random variable is the number of heads observed, how many different outcomes are there for this experiment? Now, how many different x values, right? Our random variable is the number of heads observed. We have one where we have 0 heads observed. So it can assume the values 0, 1, 2, and 3. So we can have no heads, we can have 1 head, we can have 2 heads, or we could have all 3 heads. Everybody following along what's going on here, what I'm doing? This is kind of stepping back from the homework assignment that we went over at the beginning of class. So what's the probability of each of these events? How many times does no head show up out of 8? So what's the probability that x equals 0? 1/8. So what's the probability, I'm going to skip the middle two, what's the probability of exactly 3 heads? 1/8. So how many experiments do we have left? Or how many different events? So I've used this one, and I've done that one. We have 6 left, right? And notice there's 3 that have 2 heads, and there's 3 that have exactly 1 head. So each of those would be 3, 6. So the probability of getting exactly 1 head is 3/8. I think I said 3, 6. I meant 3/8. And the probability of getting exactly 2 heads is 3/8. So what's our average number of heads we would expect from this experiment? What's our mean? Well, it was defined as the x value, so the random variable, times its probability. X times p of x. So x for the first one was 0, so 0 times 1/8, plus 1 times 3/8, plus 2 times 3/8, plus 3 times 1/8. So x times its probability, times p of x. So it's going to be 0 times 1/8, plus 1 times 3/8, plus 2 times 3/8, plus 3 times 1/8. And this falls from this example of the 2 coin toss. And I really ignore the number of times because I've already come up with the probability. And let's punch it in. So this is equal to 0 times 1/8 is 0. Or you could even write it as 0/8. Same thing. Plus 3/8. Plus, what's 2 times 3/8? 6/8, right? Plus what? Plus 3/8. Because 3 times 1/8 is 3 times 1 is 3 over 8. What do we get here? 12 over 8, which is 1.5 heads we would expect 1.5 heads in the long run per experiment. And in this case, for the 3 coin flips, the expected value really doesn't tell us a whole lot. Right? This is kind of going through the process. This next example really puts some light on why we care about the expected value. And it has to do with insurance. Right? You guys probably think, man, the insurance companies probably make all kinds of money because I'm constantly, right, paying into it and they're not really getting anything out. Right? Everybody in here pays car insurance if you have a car, and one of us might get in a wreck in a 5-year period. So that's the only time they really have to pay out. The same thing with life insurance. All right? So let's look at this example. And then I'll come back and really talk about this. So, the mean or expected value of a discrete random variable is the sum of each of the random variables times its probability. Remember, this is our sum notation. What comes first, addition or multiplication in order of operations? Multiplication. That's why I have to do the multiplication, so I do x times p of x plus x times p of x. That is not the sum of x. So I'm not adding 0, 1, 2, 3 and then multiplying it by one of the probabilities. All right? I'm multiplying each event by its probability. So that's the formula for it. And we denote it with an E. Do not associate this E with this summation notation. Those are not the same thing, even though they kind of look similar. We call mean the expected value. The expected value is the average. We expect people to be very close to their average. All right? This is exactly the type of thing that Moneyball was written about. All right? Now you wouldn't expect a guy to get on base 4 times in a single game, but as you do it over and over again, on the average, in the long run, you would expect that person to be close to their average. All right? So they'll get on 4 times one game and then no times the next game, and then 3 times one game and then 1 time, and then they end up being a 50% on base percentage. Right? You're going to be what you are in the long run. That's kind of what this expected value is. You might have some anomalies where you do it a lot once or you don't do it any in a certain event, but in the long run, you expect to be close to your average. Expected is a mathematical term and should not be interpreted as it is typically used. Specifically, a random variable might never be equal to its expected value, which is what happened here. I'm never going to get one of my experiments, right, one of my random variables to be equal to 1.5. That's never going to happen. I'm never going to have half a head. That's just what we would expect in the long run. Specifically, a random variable might never be equal to its expected value. Rather, the expected value is the mean of the probability distribution or a measure of its central tendency. You can think of mu as the mean value of x in a very large, actually infinite, number of repetitions of the experiment in which the values of x occur in proportions equivalent to the probabilities of x. So what would we expect in the long run? And here, this really puts some idea behind why we care about expected values. So let's read this problem. Suppose you work for an insurance company and you sell a $10,000 one-year term insurance policy at an annual premium of $290. So if you pay $290 a year, or what is that, about $25 a month, right? Because $240 would be $20 a month, give or take. Pretty much 25, a little bit less than that. It's probably about $24 a month. So if I took a bunch of people and enrolled them in this program, well, I'll pay $10,000 if you die, if you give me $290 a year. Now, obviously, if everybody that has the insurance coverage dies, they're going to lose money. Obviously, right? But of course, that doesn't happen. What would you expect the payout to be? All right, for the insurance company. Is the insurance company going to make money or are they going to lose money? All right? actuarial tables show that the probability of death during the next year for a person of your customer's age, sex, health, etc. So obviously they're picking healthy people because the probability that they live is very high here, right? Which is why insurance companies care if you have a pre-existing condition or if you're a smoker and all these different questions. Because that changes this probability that you're going to live or die. So who'd have thought that your insurance comes all the way back to a mathematical formula, right? So the chances somebody's going to die is 0.001 or 1/10 of 1%. Basically, 1 out of every 1,000 people will die. That's what this is saying, right? 999 will live, 1 will die. So they'll have to pay out this $10,000 only once, according to this table. So they're going to make $290 999 times, and they're going to have to pay out $10,000 only once. But they're actually only paying out $9,710 because that person still had to pay their premium. So it's really not even costing them $10,000. What is the expected gain amount of money made by the company for a policy of this type? The experiment is to observe whether the customer survives the upcoming year. Now, depending on where they live, I mean, all this stuff really has an effect on what this probability is, okay? So let's say this is a healthy person living in a rural area, right? Where there's less traffic, right? They're not driving as much because that's actually our highest probability of dying is in a car, right? So probably somebody that doesn't drive very much. The probabilities associated with the 2 sample points, live and die. Those are our 2 sample points. We either don't pay them or we do pay them, right? That's what the insurance company really cares about, which is kind of sad in one sense, but the random variable you are interested is the gain, X, which can assume the values in the following table. So here we go. So the gain from the company. So if the customer lives, the company makes $290. If the customer dies, the company makes loses $9,710. Because they still made the $290 off the customer. They still had to pay for their policy. All right? If the customer lives, the company gains $290. If the customer dies, the negative gain is $9,710. I would expect my expected value to be $290 times the probability. So X times P of X plus X times P of X. Therefore, the expected gain by the company is $280. So the company would expect to make money on this. This is how they basically adjust what the premium is. If they run this formula and their premium is too close to 0, or their expected value is too close to 0 for their comfort, they jack it up. They jack the premium up. So that when they run this formula, it makes this number be positive. Right? Because if this 290 was too small, when I run it through this formula, that's actually going to turn to a negative number. That company doesn't want a negative number. They don't stay in business that way. So the company would expect a profit on average. In other words, if the company were to sell a very large number of $10,000 one-year policies to customers possessing the characteristics described, it would average net $280 per sale in the next year. So they make $280 of that $290. Basically, only $10 of each of those premiums they lose paying out to the one person out of 1,000. So they actually make $280 out of the $290. It kind of makes you sick a little bit that they're making that much money, but they kind of have to hedge their bets, because if this number goes up even slightly, it has a drastic effect on their expected value. Right? Note that E of X need not equal a possible value of X. Right? That 280 is not equal to any of my potential outcomes, which is exactly what happened in our 3 coin toss experiment. That is, the expected value is 280, but X will either equal 290 or negative 9,710 each time the experiment is performed. The expected value is a measure of central tendency, and in this case represents the average over a very large number of one-year policies. but it's not a possible value of X. So this is how the insurance company determines how much to charge for a premium. They run it through this formula. X times P of X plus X times P of X. So they're really pretty straightforward, because in these examples on your homework, you'll be given your X and your P of X. You'll just have to multiply them together. You'll just have to do the arithmetic behind it. But you'll be given these values. Okay? So that's how you find the mean of a discrete random variable, which is a measure of central tendency. So I want to know how much it's going to vary. So I average 280 per sale, but what's my standard deviation? Is it large or is it pretty small? There's actually a formula for standard deviation, which I'm not really going to go through the derivation of it, but here it is. Here's our formula for the variance, and then the standard deviation, of course, is just the square root of it. So notice how it has mu in here. This mu is the expected value. That is sum of X times P of X. All right? So our variance, right, of a random variable X so variance of a random variable X is, it's always denoted by sigma squared, which is equal to the sum, that's an ugly looking sum symbol, the sum of the squared X values times P of X. So notice I have to do kind of one more step, right? Because mu was equal to X times P of X. So the sum of each of the values squared times P of X minus mu squared. And remember, mu is X times P of X, the sum. So I could rewrite it this way. Minus the sum of X, P of X, quantity squared. Doesn't that kind of look like our formula, our shortcut formula? Because remember how one we had to square the terms and then add them, and the other one we had to add them and then square it, right, in our variance formula? These two things are the same. I've just replaced mu with its formula, the sum of X times P of X. And then you need to square the entire thing. So notice how I put it in parentheses and then square it. So notice this piece and this piece are exactly the same. And then the standard deviation is just going to be the square root of the variance, right? So we have the mean of a random variable, which is equal to the sum of X times P of X. And we have the variance, and then the standard deviation is just the square root of the variance. So here's the two formulas from this section. And notice you have to know mu, which is equal to this. So I've rewritten the variance formula where you don't have mu. But it's the same thing. So this is the mean, and that's the variance. Mean or expected value. Okay? So let's do an example of this. And then it talks about Chebyshev's rule, which is the same stuff. It's nothing new. And it says the standard deviation is just the square root of the variance, which is nothing new. And then you can apply Chebyshev's in the empirical rule. Let X be a discrete random variable with the probability distribution P of X, mean mu, and standard deviation sigma. Then, depending on the shape of P of X, the following probability statements can be made, which is stuff we've already seen. So, within one standard deviation of the mean, we would expect 0 for Chevyshevs, right, when we don't know anything about the shape. If we do know it's approximately normal, we would expect approximately 68% of all observations to be within 1 standard deviation of the mean. So this stuff is the same, right? Nothing's new right there. Okay. And then here's a skewed and a mound-shaped symmetric, right? Nice review. This is skewed to the, which direction? To the right. The tail is to the right. Okay, let's do an example. This is just like what we're going to have on our homework, okay? Finding mu and sigma skin cancer treatment. All right? Everybody in here probably knows somebody or is even related to somebody who's had to deal with skin cancer in some way or another. Especially living down here in the desert Southwest, right? We really got to worry about the sun. Right. Medical research has shown that a certain type of chemo is successful 70% of the time when used to treat skin cancer. And that medical research came from a clinical trial, right? So they performed a clinical trial, and they showed in the clinical trial that 70% of the time the chemo worked. Suppose 5 skin cancer patients are treated with this type of chemo. So X is my random variable, and I'm going to let it equal the number of successful cures out of the 5. Does everybody see that the random variable X is not the same as its probability? The random variable is the number of survivors. Its probability is the chance of you getting that number of survivors. Okay? So here's our table. And notice these tables will be given to you on your homework, all right? This type of stuff. Okay. The probability distribution for the number X of successful cures out of 5 is given in the following table. So the way that they came up with this is they basically performed the experiment of looking at 5 skin cancer patients an infinite number of times and then recorded the probability of survivors. So you're not really concerned with how they came up with these probabilities. All right? Just take that they're true, they're it, that's what we're going to use. So X is the number of successful cures. So the chances that all 5 people will die is 0.2%, which is pretty low. Now, look at our number of 70%. What is that pretty close to out of 5? What out of 5 would be the closest to 70%? 2 out of 5? 3 out of 5? 4 out of 5? What is 4 out of 5 on the calculator? What is that as a decimal? 80%. What's 3 out of 5? It'll be 60%, right? So we would expect about 3.5. Does that make sense? We would expect about 3.5 survivors because that's 70% of 5. Where you notice the 2 most likely outcomes is either 3 people survive or 4 people survive. Look at the probability. If I add those 2 probabilities together, I get, what, 66.9 or 67%. Basically, 2/3 of the time I would expect either 3 or 4 survivors. So most of the time, somebody's going to die. I mean, that's just the fact of the matter. Only 17%, which this rounds to, right, or 16.8% of the time, all 5 survive. So basically, the rest, right, 83% of the time, I would expect at least 1 person to die. That's what that's saying, okay? So let's look at our mean, our expected value, which I would expect to be 3.5, because 3.5 is 70% of 5. So if 70% of the time is successful, then I would expect 3.5 people to survive out of 5, right, in the long run, because that's 70%. So let's do it. So A says find mu, which is equal to and that's E, not sigma, the expected value of X, which is equal to the sum of X times P of X. Okay? So this is equal to, so the sum of X, so this times this, plus this times this, plus this times this, right? All the way out. So that's equal to 0 times 0.002. And really, I don't even have to write this down. I know it's going to be 0, but I'm going through the whole systematic approach of finding this. Plus 1 times 0.029 plus 2 times 0.132 plus 3, I'm running out of room here, 3 times 0.309. Now this is not something I would expect you to do in your head. Put this in your calculator. 0.36 plus 5 times 0.168. And a lot of your calculators will do expected values. All right, so let's do that. So I'm not even really going to be concerned with this one. I'm not even going to worry about putting it in the calculator. I know it's going to be 0. So let's do 1 times 0.029, which is just 0.029. So 0.029 plus 2 times 1.132. And I don't have to worry about order of operations or any parentheses because it'll do the multiplications before it does the addition. So 2 times 0.132 plus 3 times 0.309 plus 4 times 0.36 plus 5 times 0.168. What do we get? 3.5. So our expected value is 3.5 survivors out of every 5 people that get this skin cancer. And even though our expected value is not one of the random variables, that doesn't matter. Okay? Let's do part B. Let's find the variance. Where the variance was equal to, I have it written right here, the sum of x squared times p of x minus mu squared. I've already found mu, it was 3.5. So let's do this formula. Oh, it wants us to find standard deviation, but I'm going to find the variance first, and then I'll square root it. That's why it has this square root over the top. Okay. So there's the mean, which is 3.5. So my variance is equal to the sum of x squared times p of x. Is it plus or minus? Minus. Okay. Minus mu squared. Of course it's minus because this is minus. Right, it's the sum of the differences, the squared difference. So my variance is equal to 0 squared plus 0.002. All right, let me write this over so I can try and fit it all on one line. So it's 0 squared plus, or times 0.002 plus 1 squared times 0.029 plus 2 squared times 0.132 plus 3 squared times 0.309 plus 4 squared times 0.36 plus 5 squared times 0.168. Now, all of this has to get added together first before I do the subtraction. Right? It really doesn't matter because of order of operations, but just something I want you to get used to. Minus, what was mu? And what was our average that we found in part A? So minus 3.5 squared. So variance. Put that in your calculator. So I don't even need to worry about this piece. I'll just ignore it. This one is just still 0.029, right? Because 1 squared is still 1. So 0.029 plus 2 squared. And the nice part is I don't have to worry about parentheses on that part. plus 2 squared times 0.132 plus 3 squared plus 3 squared times 0.309 plus 4 squared, and I didn't even put a times in there. Plus 4 squared times 0.36 plus 5 squared times 0.168. So what I'm going to do here, what I have written here is what I have in brackets here. Does everybody see that? So I'm just going to go ahead and hit enter. So it equals minus 3.5 squared minus mu squared. And then hit enter. So my variance, that is not my standard deviation, that is my variance. What's my standard deviation? What do I have to do to get it? Square root, right? So I'm going to go second, square root, second answer. So it just pulls that decimal. Or I could have typed the decimal out. But I prefer you guys to get in this habit because sometimes these decimals are really long, right? And they don't end. And hit enter. Let's do it out to 2 decimal places. So what's that going to be? 1.02. So my average number of deaths is 3.5, give or take 1 death. All right. So my standard deviation is 1.02. So if I go 1 standard deviation above 3.5 and 1 standard deviation below 3.5, which I don't really know anything about the shape of this, so I couldn't say that 68%. Then it has the graph down at the bottom. So here's the graph. And then let's answer part D once we look at the graph. So I'll look at the graph using that mean and standard deviation. So it says graph P of x, locate mu in the interval mu plus or minus 2 sigma. So 2 standard deviations above the mean, 2 standard deviations below the mean. Use either Chebyshev's rule or the empirical rule to approximate the probability that x falls into this interval. And then, would you expect to observe fewer than 2 successful cures out of 5? What do you guys think? Would you expect to observe fewer than 2 successes? Or would we expect more than 2 successes? What do you think? More. Definitely. We would expect more. I mean, the average is 3.5 successes. So I would definitely expect fewer than 2 to be a very small value. So here's my mu, 3.5. The sum of x times p of x, which is 3.5. And then they do the variance, which I have written on the board over there. Now they don't use the same formula I did. They get the same thing. They got 1.05, and then the standard deviation is the square root of it, which is 1.02. And then they do a 2 sigma confidence interval, basically. 2 standard deviations above the mean would be 5.54. 2 standard deviations below the mean would be 1.46. So within there, x equals 2, 3, 4, and 5 all fall within that interval, right? 0 successes and only 1 success isn't in this 2 sigma interval, right? It's below. Because 1.46 is my low end of it. So within 2 standard deviations would be the probability of x being 2, 3, 4, and 5 all added together. So I would expect 97% of these experiments to fall within 2 standard deviations of the mean. The rest of that, x being 0 or 1, would fall outside of it. We'd only expect that to happen, what, 3.1% of the time? Which is adding together when x is 0 and when x is 1. Right there? 0.031. Fewer than 2 successful cures implies out of 5 that x is either no successful cures or 1, because it says fewer than 2. It doesn't say fewer than or equal to 2. Right? Or if it would have said at most 2, at most would it include 2. And then here's the distribution. So it's skewed a little to the left, but it's still approximately normal because definitely, remember the empirical rule said what percentage had to fall within 2 standard deviations? You guys remember? 95%. And what percentage fell within 2 standard deviations of that experiment? 96.9, right? So it definitely, this number has to be approximately 95%. It's actually a little bit more. So I would say that this is approximately normal. And if I went back and did 1 standard deviation, so 1 standard deviation would be what? It'd be 4.5 and 2.5, right? So 3 and 4 would be included within 1 standard deviation. What's the probability of 3 and 4 added together? That'd be 0.669, which is 67%, which is dang close to our empirical rule. We had 67%, and the empirical rule is approximately 68. So it definitely fit 1 and 2. I would definitely expect it to fit 3, or be very close to 3. It's actually not going to be exactly 3 because our 0 is going to be out. Isn't going to be included. But it was 99.7 if you remember correctly. Not 100%. Okay. So a lot of fancy talking there for really just a pretty straightforward formula. Like the formula is really not that complicated. Coming up with these probabilities would be very complicated, but luckily we don't have to do that, right? They'll already be given to us. Okay. That's the end of that section. So a lot of this same stuff, right? And I want you to pay attention to this terminology. X is less than or equal to 1 is only x being 0 or x being 1. When we get to continuous, we got to pay attention to that inequality symbol. It's different for discrete than continuous. We're only dealing with continuous now, up to this first test. Okay. So this is the truth for any discrete random variable. It doesn't matter the number of outcomes, all right? There could be 2 outcomes where somebody survives or somebody dies. There could be like our coin toss experiment where there was 4 or 5 different outcomes. Doesn't matter how many outcomes there are, right? In this case, there was 6 different outcomes. You could have had 0 people die, 1 person died, or survive, not die. Right? The number of outcomes in this experiment, there were 6. 1, 2, 3, 4, 5, 6. 6 different things could happen. Now we're actually going to look at something that makes this smaller. We're only going to look at experiments that only have 2 outcomes. Either success or failure. So it really follows that insurance one, right? Where it only had 2 outcomes. You either survive or you die. Or you call surviving success and failure dying. Okay? So when we look at experiments that only have 2 outcomes, they have a special name. Binomial random variables, right? So let's start this section. The formulas for this, for finding mean and standard deviation, are even more simple than the regular discrete random variable stuff, the expected value. They're actually a little simpler. Actually really easy. It's just 1 multiplication. Binomial. The root word bi, like on bicycle, means 2. Nomial means number. So this means 2 numbers. That's it. That's what binomial is. 2 numbers. Have you ever heard the word dichotomy or dichotomous? That means you're caught in one of two things, one or the other. Right? And I've said that word when I talk about polling, getting good data from polling people about an election. There's a dichotomy where you don't want humans making the selection of who gets included in the study, but you do want humans asking the question. Because people are more likely to answer a human than will pop up on your computer screen. So that's the dichotomy of polling. And the dichotomous responses, i.e. responses for which there exist two possible alternatives, such as yes, no, pass, fail, defective, non-defail, male, female, and so on. So binomial only deals with two outcomes. A good example is shooting a free throw. You either make it or you miss it. All right? You can't have half a free throw go in. Now, your expected value of free throws made, given a certain number, could be a decimal. But for each event, you would expect a whole either success or failure. Okay? Or your percentage of successes might be a decimal. A simple example for such an experiment is the coin toss. A coin is tossed a number of times, say 10. Each toss results in one of two outcomes, a head or a tail. So if you're at the beginning of the game and you're calling heads to get the ball, heads would be success, tail would be failure. Right? Ultimately, we are interested in the probability distribution of X, the number of heads observed. Right? How many successes are there in 10 trials? How many free throws do you make out of 10? How many successes are there? That's what we're kind of talking about here. Okay? Many other experiments are equivalent to tossing a coin, a fixed number n times. So n is the number of tosses. We're actually going to use our combination formula here, which is nice that we've already learned it, right? And observing the number x of times that one of the possible two outcomes occurs. Random variables that possess these characteristics are called binomial random variables. Binomial means there is only two outcomes. Remember, the definition of a random variable just means that each of the outcomes are assigned a probability. There could be 15 outcomes. Binomial really concatenates that down to where there's only two outcomes. Public opinion and consumer preference polls frequently yield these observations. Do you like it or do you not like it? Right? One of two outcomes. Okay? Suppose we are interested in X, the number of students in the sample who favor a given issue. All right? Whether they favor a head or a tail. I'm sure everybody in here, when you do a coin toss, you probably pick the same thing every time. Right? That's just human nature. All right? Me, when I do a coin toss, I always pick tails. Because of the saying, tails never fail. Now, that is absolutely not true. It fails half the time. All right? But that's just what I do. I always pick the same thing. And most people are that way. Sampling 100 students who likes heads and who likes tails would be a binomial experiment. If you like heads, we'd say that's a success. If you like tails, we'd say that's a failure. So if it has two outcomes, it's a binomial random experiment. Okay? So that's what I want you to remember. Two outcomes. Binomial means two outcomes, success or failure. So here's the characteristics. Let's write these down. We've got about 20 minutes left, and then we can get out of this hot box. All right? Look, on the bright side, you don't have to go exercise after this because you've lost weight. All right? The experiment consists of n identical trials. If I'm shooting free throws and then I go back and shoot a three-pointer, I can't include that in the same experiment. They have to be the exact same trial. So 1, the experiment consists of n identical trials. N identical trials. You have to do the same thing. I can't ask one person, do they favor heads or tails, and then ask another person, do you like blue or green? That's not the same trial, right? So 1 is n identical trials. There are only two possible outcomes. those possible outcomes we call either success or failure. And failure doesn't mean you've done something bad or something wrong. It just means it's the opposite of success. All right? Whatever we define success, the opposite is failure. All right? Number 3. Let me put a star there instead. S is always equal to P. The probability of success is P, and F is equal to Q, which is just the complement of P. You guys remember seeing this in 106? If our chances of being successful are, say, 70%, then our chances of failure are the complement of that, 30%. Right? It's complement. Notice in this formula, if I add P and Q together, it always equals 1. So your chances of success plus your chances of failure is always 1, which makes sense, because there can't be a third thing that happens, right? So we'll call it lowercase p, and failure we'll call Q. Q is simply 1 minus your probability of success. Right? Pretty straightforward stuff, really, once you understand the notation. Number 4. This is really why I covered section 3.6, because 3.5 and 3.6 are not going to be on the test. But we have to have an idea and a notion of what independent means so that I can even go over number 4 right here. Right? Number 4 means what happened the first time has no influence on what happens the next time. If I flipped ahead, that has no influence on what I get on my next flip. Rolling dice are independent, okay? That's not mutually exclusive, because I could get the same outcome on 2 events, right? Which means they do have something in common. It just means what happens the first time has no influence on what happens the second time. Trials are independent, which you would expect on, say, on a roulette wheel. Really any of the casino games, except for the slot machine. The slot machine, the rolls are not independent. The slot machine knows if it paid out on a roll, that influences how it pays out the next roll. So they're not independent, which is another reason why the probability of winning goes way down. A roulette wheel is definitely independent. Right? If I got a 22 on roulette, what I get the next time has absolutely nothing to do with me getting a 22 the time before. Even though a lot of people will look at the stream and say, well, 12 showed up, I'm going to bet 12 again. There's no chance. There's absolutely no chance that you'll get 12 any more than you'll get any other number. Now, if 12 starts showing up a lot, you probably got a wheel that's not fair. That there's some type of weighting going on, or maybe the ball's not fair. The binomial random variable x is the number of successes in n trials. So x is the number of successes. How many free throws did I make? Okay? So my random variable x is number of successes. There's not really a specific name for the number of failures. It's just what's left over. So x could be equal to n, because I could be successful every single time if I made all 10 of my free throws. All right, 10 out of 10. All right. This talks about Jacob Bernoulli, who's really spent a lot of time with this. A Bernoulli trial is one that's either success or failure. This is really that thing I was talking about with the stock market. That part of it's a 50-50 proposition. You know, there's a lot of stuff that deals with the economy and things like that. But part of that formula for determining if a stock's going to gain or fall is a Bernoulli trial. It's a simple coin flip. It's a success or failure. Right? So, you know, anytime you hear Bernoulli trial, that means there's one of 2 outcomes. And you'll probably hear this a lot, you know, when you get into your fields, right? When they're trying to come up with something, you know, if you're determining fish in a stream, if you're a wildlife and fisheries major, right? you know, and you're coming up with the catch and release standard, right? How big does a trout have to be before you don't have to put it back, right? Before you can keep it. Well, that's a Bernoulli trial. Is it above or below 20 inches or whatever the number happens to be? That's how they determine how big a fish needs to be before you can keep it. Is what's the length of all the other fishes? What's the length of all the other fish compared to that one? So Bernoulli trials show up all the time. Just deals with 0 or 1 is what they call them. 0 does happen, 1 doesn't happen. Or vice versa, depending on your experiment. So here's some examples. Let's decide whether they are a binomial random variable. Does it lead to one of only 2 possible outcomes? That's the definition of binomial. 2 possible outcomes, right here. Number 2, 2 possible outcomes. We call the outcomes success or failure. A university scholarship committee must select 2 students to receive a scholarship for the next academic year. The committee receives 10 applications for the scholarships, 6 from male, 4 from female. Suppose the applicants are equally qualified so that the selections are randomly made. Let X be the number of female students who receive a scholarship. How many possible outcomes are there for this experiment? How many possible females could I get that get a scholarship here? 4 or, well, we're giving away 2 scholarships. There's 4 different females, but if I let X be the number of females who receive a scholarship, I'm only giving out 2. So what number of females could I get from giving out these 2 scholarships? I could either get 0, 1, or 2. I can get 3. There's 3 different outcomes. So that's obviously not a binomial experiment because there's 3 outcomes. Because it's possible that they could both be male, one of them could be female, or both of them could be female. So X could assume 3 different values here. So that kicks it out of it being a binomial experiment. That make sense? Okay. Now, if I said I'm giving 1 scholarship, and I said let X be the number of female students who receive a scholarship, it would only be 0 or 1. That could be a binomial experiment. Because either a female gets it or a female doesn't get it. That's success or failure. That's only 2 outcomes. Okay? Let's see, because I don't want to really go over all of these, but let's do both of them. Before marketing a new product on a large scale, many companies conduct a consumer preference survey. Makes sense, right? And you see it a lot, especially with like Lay's potato chips. You know, they have these where you make your own flavor. And they kind of send small batches out to small communities to see if people like them or not before they do it on a large scale. Right? Suppose a company develops a new diet soda and then conducts a taste preference survey in which 100 randomly chosen consumers state their preference from among the new soda and the 2 leading sellers. Let X be the number of 100 who choose the new brand over the 2 others. How many different outcomes will there be in this experiment? Now, I'm not asking how many different people will give an outcome. How many different responses will I get from those 100 people? They either what? Like it or don't like it. This is a binomial experiment. They either prefer it or they don't prefer it. So this is definitely a binomial experiment. Okay? One of 2 outcomes, success or failure. In this case, you would call success them liking it, and you'd call them failure them liking one of the other 2 flavors. Okay? Okay, and this is a nice one because we have fiber optic here in Portales. Some surveys are conducted by using a method of sampling other than simple random sampling, which is where everybody goes in a hat and you draw somebody out, right? Everybody is equally likely to be picked. For example, suppose a television cable company plans to conduct a survey to determine the fraction of households in a certain city that would use its new fiber optic service. So if I have 100 households, what percentage of those households would use my fiber optic service? I think here in Portales it's about 40% are on the fiber optic. The other 60% are using Quest or DirecTV or Xfinity cable. There's different types of internet. The sampling method is to choose a city block at random and then survey every household on that block. So that was their sampling method. This is called cluster sampling. You don't need to worry about that definition. That's just what this particular type of sampling is called. Suppose there's 10 blocks sampled, producing a total of 124 responses. Now you would hope that of these 10 blocks that are sampled, right, that those 10 blocks are characteristic of the city as a whole. Right, a few from the rich neighborhoods, a few from the poor neighborhoods, a few from the middle class neighborhoods. Let X be the number of 124 households that would use FiOS. How many responses are there for X? How many values can X assume? Yeah, one of two, right? They either would use it or they wouldn't use it. This is definitely a binomial experiment. Okay? Yes or no? Success. Now, there will be 124 different X's, right? There'll be 124 different responses. But of those responses, I'm only getting one of two things. They either want it or they don't. So I would need to count how many want it, right? And hopefully that's more than half, or that would at least be a number that would pay for me even doing this. Because installing fiber optics is not cheap, right? It's all hardware. It's not wireless. Fiber optic itself isn't cheap. At first. In the long run, it becomes really cheap because it moves a lot of material, right? A lot of information can be transmitted through fiber optics. Okay? All right, let's do one more example, and then I'll look at the... So I'll probably have to touch tomorrow talking about the formula for this. But it's really just a plug and chug, right? You plug in values and chug it through the formula, okay? So the Heart Association claims that only 10% of U.S. adults over age 30 meet the minimum requirements established by the President's Council for Food, Sports, and Fitness, Sports, and Nutrition. Only 10% of U.S. adults over 30. That's a pretty low number here. You know, we probably all did this at one time in high school. That's really been around for a long time. And if you passed that test, you went to the skating rink or something, they took you out for something cool. You had to do like the chin-up bar and do so many chin-ups or hold it for so long, and it was different for males and females. Suppose 4 adults are randomly selected and each is given the fitness test. Now, if only 10% of U.S. adults meet the requirement, how many of these 4 adults would we expect to pass? What do you guys think? None. I wouldn't expect any of them to pass. Because if one of them passed, that would be 25%, right? 25% is farther away from 10% than 0 is from 10%. So I would actually expect none of these adults to pass the test. This is a binomial experiment, right? Because you either pass the test or you don't pass the test. You either pass or fail. I would expect of these 4, none of them to be the most likely occurrence. Which is kind of sad, but that's the truth. Now, that's assuming that this 10% came up with, right? They came up with this 10% in a very valid way. All right? And I'm sure this varies from state to state, region to region, city to city, this varies. All right? Actually, Albuquerque is one of the more fit cities in the entire United States. Now, New Mexico as a whole isn't, but the city of Albuquerque is. Then you go to Texas, and it's like the most obese on average in the entire country. All right? So it definitely depends on where you're at. We'll change this number. Okay, use the steps given in Chapter 3 to find the probability that none of the 4 adults passes the test. And we'll just kind of go over that, okay? So, the first step is to find the experiment. Passing is success. Failure is failing. Next, we list the sample points associated with the experiment. Each sample point consists of the test results of the 4 adults. For example, SSSS represents the sample point denoting that all 4 adults pass, while FSSS is 1 fails, and so on, right? So I'm not really concerned with you being able to come up with those as of right now, okay? It's listed on the next page. which is right here. So we would expect each of these to be equally likely. How many different outcomes are there? Should be 16, right? This is just like the 4 coin toss thing that we started class off with. Notice how it's 1 out of 16, 4 out of 16, and 6 out of 16. So if we expect each of those outcomes to be equally likely, or not equally likely, because failure, the chances is 90%, success, the chances is 10%. So these aren't equally likely, right? But they don't have to be equally likely. It never says that. So the way they do it, the probability of SSSS is 0.1 times 0.1 times 0.1 times 0.1. Right? Because chances of success is 1/10. So it's the intersection of all 4. The chances that all 4 would be successful is 1/100 of 1%. Not very likely. And these are all independent events. That's why I can multiply their probabilities together. Remember, if an event is independent, then the multiplication of each piece separately, right, is equal to the probability of the intersection. That's another reason why we covered that section, so I could talk about this. Right? So then I would want to do, so this is my probability for one failure is 0.0009, but then I'd add it together 1, 2, 3, 4 times. Because that's 0.009, that one's 0.009, that one's 0.009, and that one's 0.009. Okay? So as I go through and find this out, so your chances that all 4 adults fail is 0.9 times 0.9 times 0.9 times 0.9. There's actually a 66% chance that every adult will fail, which is that's pretty likely. That's probable. That's over a 50% chance. So basically what you would say is you would bet on that. You would bet that all 4 adults would fail this test. Before you would even bet that at least one would pass. Because at least one would pass would be the complement of this, which would only be, 34%. And that includes 1 passing, 2 passing, 3 passing, or all 4 passing. So this leads us to the conclusion that we're not in very good shape. Right? That 10% number is way too low. The chances that 3 of the 4 adults pass is each of the probabilities added together. So 0.1 times 0.1 times 0.1 times 0.9. So they do 0.1 times itself 3 times, so that's why it's 0.1 cubed. And each of those have the same probability, so it's adding the same thing to itself 4 times. So look at that number. So 0.3% of the time you would expect 3 of the 4 to pass. Not very high. Very low numbers here. Now what I want you to kind of look at here is the way that we're going to build this formula comes from this. Right? It kind of leads back to that Challenger example I went over. Right? Each of the bolts had a 98% chance of success. But if even one of the bolts failed, the entire thing blows up. So our chances that at least one fails was 0.9 times 0.9 times 0.9 times 0.9. Or the chances that all 4 would succeed, which is what has to happen. Because if even one fails, the whole thing fails. So we saw that probability, even though it was 98% for each bolt, when we did all 4 together, it was like 88%. That's why we had failure. All right. And what this leads us to is the number of sample points for which x is 3. So 0.1 times the number of successes, which was 3, right? 3 successes in our test, times 0.9 times the number of failures. So notice this is our probability of success to the number of successes times the probability failure to the number of failures. So see how the exponent is the x value? And in the parentheses is the probability of the x value? We can rewrite this in a general form. Do you have a question?
Where did you get the probability of the success?
failure?
It was given to us at the very beginning.
It was given.
Yes. Yeah, it was right here, the very first line.
The 10%.
Yep. What's 10% is a decimal? 0.1. Right. Yeah, that number would have to be given to you. There's no way you could come up with that. Okay. So our P, our probability of success, is 0.1, which is defined right here. So S is 0.1. Failure would be 0.9 because it's 1 minus 0.1, right, which is 0.9. Now, the nice thing about this is once you know probability of success and then the number of successes, you just jam it through a formula. Right? That's all we're going to do here. And then here's the formula. So here's building it up. So the number of different ways of selecting 3 successes and 4 trials. So this is a way of coming up with the number of events in which there were exactly 4 successes. Exactly 3 successes, excuse me. Notice that's just our combination formula that we've already learned. Okay? So it's the combination. So the number of successes, of 3 successes and 4 trials, times the probability of its occurrence is what's going on right here. Right? So in general, I could put any number in for X and let that be the number of successes in N trials. So let's do this example for 0, because didn't we think that 0 would be the most likely? Right? So let's do it for 0. So I'll put it right here on the next one. So I want to know the probability that everybody fails. All right, so what's the probability of X equals 0? So that's going to be out of 4 people, how many successes do I have? 0. That's the number that goes there. Times 0.1 to what power? What's listed right here? So notice how the number of successes, right? Because this is the probability of success. So the exponent is going to be the number of successes, which is 0. What's our probability of failure? 0.9. And how many failures were there? If there were no successes in 4 trials, then that means there's 4 failures in 4 trials. So let's punch that in the calculator. What's 4 choose 0? And this is where you have to know 0 factorial. So 4 factorial over 0 factorial. What do we say 0 factorial was equal to? It has to be 1. It can't be 0. If it was 0, then this would be undefined and you couldn't go any further. And then right here is 4 minus 0, right? So it's 4 factorial. What is that going to reduce to? What's 4 factorial over 4 factorial? 1. So this is just 1. There's one way that you can pick no items from 4, right? There's only one way in which you can have 0 successes from 4 experiments. Times 0.1 to the 0. Which, what is 0.1 to the 0? What's anything to the 0? 1. Times 0.9 to the 4th. Maybe I shouldn't write that way. So this is equal to 1. You said this is equal to 1, right? This piece. 0.1 to the 0 is 1. Times, what's 0.9 to the 4th? 0.6561. So that equals 65.61% of the time. So if I randomly selected 4 adults, 65% of the time, none of them would pass this experiment. None of them would pass this fitness test. Now notice if I added together the probability of none of them passing, plus the probability of exactly 1 passing, plus the probability of 2 passing, plus the probability of 3 passing, plus the probability of exactly 4 passing, which would be the lowest, what do you think that's going to equal? Is there any other possible outcome for this experiment? If I go and test 4 people, either none of them can pass my test, 1 can pass, 2 can pass, 3 can pass, or all 4 of them can pass. So what's that going to sum to? 1. 100%. Because there's no other possible outcome here. Right? And then there's the description of the formula. Number of simple events in X successes. Probability of X successes and N minus X failures in any simple event. So notice here they put 1 minus P instead of Q. Where I actually just put Q. The way they come up with Q is 1 minus P. All right. Then we'll end right here. So here's the formula. So this assignment 10-4, or 4-4, excuse me, 10-4. 4-4 is due tomorrow by midnight. What we're going to do tomorrow is review for the exam. All right, the exam will be Thursday. I have a feeling we're going to spend most of our time talking about this probability stuff, or the discrete probability distributions, the chapter 4. So today we learned about expected values, and then we learned about the binomial probability distribution, which is an event that has only 2 outcomes, either success or failure. That expected value works for an event that has any number of outcomes. All right. And the way you do this on your calculator. So let me do this number on my calculator just to show you. So I'm going to punch P of 0 into the calculator. All right? So the way I'm going to do it is I'm going to do 4 choose 0. If I hit my PRB button, notice how it has the NCR right there? So it'll do the combinations formula for me. So I'm going to go back to that screen. I'm going to go 4 probability NCR choose 0 and hit enter. What number should I come up with right here? 1. Better be 1, right? And it is. Okay. And then I'm going to go that number times. So notice how I just hit the times key and it pulls up whatever your previous result was. So I'm going to go times 0.1 to the 0. The way you do to the 0 power is this caret button. So I'm going to do 0.1 to the 0 times 0.9 to the 4th. So I better get 0.6561 when I hit enter right here. Right? So let's do for exactly 2 people. What are our chances that exactly 2 people will pass this test? So it's going to be 4 probability, 4 choose 2. I'm going to go ahead and hit enter. There's 6 different ways that'll occur, which shows up from that one table, right, of the FFSS. So I'm going to do 6 times 0.1 to the, how many people succeeded? 2. Times 0.9 times how many people failed? Or to the, how many people failed? 2, right? And then hit enter. So I basically have a 5% chance that exactly 2 people will pass this test, which is not very likely. And I can even do it for 1. So I would expect my probability for 1 person passing should be between 0.65 and 0.0486, right? You guys agree with that? So let's do it for 1. Since we can do it so quickly. So 4, choose 1. There's going to be 4 different ways to do that. So 4 times 0.1 to the first, so 1 success, times 0.9. If there's 1 success, how many failures are there? 3. About 30% of the time. Which is in between 65% and 5%. So about 30% of the time, you would expect 1 out of 4 adults to pass the test. And you have to be careful in how this is randomly chosen, right? You wouldn't want to go pick 4 adults at Canon, right? Because they're more likely to be in shape, right? Because they've had to pass physical tests to even be there. So if I did this so I've done it for 0, 1, and 2. If I did it for 3 and 4 and then added all these probabilities together, it would equal 1. Exactly. Okay? I know I went over a little bit, and we packed a lot in today, but this is a good Monday discussion because we're all kind of rejuvenated from the weekend. And then it's all downhill from here, right, which is nice on a Monday. So tomorrow we're going to review. I want you guys to get in and get on your homework tonight and come with questions tomorrow. I mean, I'll be fine if you just want to ask homework questions for the whole 2 hours tomorrow. Okay? Tomorrow is the time to get your stuff you're not sure about cleared up. Okay? That's why we review. So you can ask me questions and I can answer them so we can clear up your misunderstandings. But you'll notice both the formulas we've talked about today, you kind of just plug and chug, right? You put the thing in the right place and then keep going. So I'm not going to make you guys memorize these formulas, but I will make you memorize where stuff goes. Okay? So tomorrow what I'll do is I'll answer homework questions, and then we'll start talking about, and then I'll go over this review right here, which I'm not going to print out for everybody. I just want you guys to bring it in. So hopefully we'll have some time in the computer lab and you can print it out. But here's section 4.4. This is the stuff we talked about today. We haven't really talked about less than or greater than, but it's just the sum of the probabilities. If it said X is less than or equal to 1 person passing, that would be the probability of no people passing plus the probability of 1 person passing. Right? Oh, then we even got to hear how many we got. So that's where we'll end class with, or we'll start class with tomorrow. But look how simple it is. To find the mean of this probability distribution is just simply the number of events times the probability. Really simple formula. So for here, my average number of people that would pass would be 4 times 0.1, or 0.04. Right, 4 times 0.1? Oh, it's 0.4, not 0.04. So the average number of people I would expect to pass this experiment, to pass this physical test, would be 0.4 people. So out of 4 people taking the test, I would expect 0.4 to pass, which doesn't even round up to 1, right? Which means 0 is our most likely thing to happen, which is supported by all the stuff we've done today. Okay? And look what the variance is. It's just n times the probability of failure times the probability, or no, n times the probability of success times the probability of failure. N times p times q. Which those are really straightforward. That's about the most simple formula for mean and variance that you'll see in the entire book. And you'll have that on the test, all right? You'll have those formulas. You won't have to memorize them. Those are a lot simpler than the formulas for expected value and for variance, right? These ones are a lot more complicated than the ones for the binomial. Okay. That's it. We're over by about 10 minutes, so sorry about that. But I will email this lecture out here in a minute, right, when I get to my office. So I know we've kind of covered a lot of stuff. I know this class moves pretty quickly. We basically covered these 2 sections in a week and a half, right? So, which is kind of what we've got to do to stay on pace for the rest of the semester. Okay.
Is the review going to be due tomorrow away?
No, the exam, the quiz review on my math lab will be due Thursday at 9 a.m. not Thursday, Wednesday at 9 a.m. when we take the test. So it's due. So really, you can get up Wednesday morning and do that to kind of practice for the test. You know, because you can do those quizzes over and over. Because for me, that's the best time to study is the morning before the test. Get up about 6.
So the test is Wednesday?
Get up about 6. Have a cup of coffee. You know. What's that? The test is Wednesday.
It is Wednesday?
So you won't miss it.
Okay.
Yeah, it'll be in class on Wednesday.
Thursday, are we starting?
Thursday we'll start the next section. Yeah. Because I had to fit a day in for the review, the final review.
Oh, we didn't have that.
Yeah, there wasn't a day for that. So I found a day in this week where we can catch up a day so that I'll have it at the end.
Okay.
But now you don't have to come later on Wednesday, you know.
Do what?
Now you won't have to come Wednesday afternoon to take the test like you were planning on doing.
Can I send
I
you?
had a
Yeah.
question on homework, and I don't know.
Let's go to my office and then I'll answer it for you.
I don't remember which one it was. I need to go through.
Oh, really? Okay.
Yes, because I had it pulled up, and I went to write it down, and I left it in the house.
Oh, okay. Yeah, okay. Yeah, we'll go get it. I'll be in my office.
Okay.
Okay. Yep.
All right. I'll see you tomorrow.
Yep.
Oh,
Question?
did you see? Oh, just got the. You watched the.
The U.S. Open? Yeah. Yeah, Johnson, man, that guy, he's had a lot of bad stuff like that happen to him. But he missed a bunch of putts, too. And see, that's something we can do. It's definitely a binomial, is making putts. Because I think the chance of success from 3 feet on the PGA Tour is like 98.8. So the chances that he would miss that putt was like 1.5%. And he missed it. Which, those greens were a little bumpier, so those averages probably were a little bit smaller than the tournament as a whole. But the chances, once he was on the green, the probability that he was going to lose the tournament was like 1/10 of 1%. And he still lost. So that's an interesting way to think about it. We'll see you, man. Yeah, let me know if you have any questions.